Transmission networks consist of numerous nodes and branches. The systematic way to study the network behavior is nodal analysis. When it comes to voltage, it is the difference that matters. So we choose a reference node, and then the number of variables are equal to the number of equations. The KCL equation at the reference node is redundant because it's a linear combination of equations at other nodes. The choice for a reference node is arbitrary, but we usually choose the ground because the ground has the most nodes connected to it, which simplifies calculation. Then we label nodes and specify reference directions for branch currents. Next, we can write KCL equations for all the nodes except the reference nodes. That is, the summation of current injection at each node is 0. If there are current sources, we'll put them on the right-hand side. Branch currents can be represented by branch admittance and node voltage according to Ohm's law. The current sources remain the same. After this, we can organize the equations in matrix form, YV equals to I. The vector I here denotes current injections from the ground to each node by current sources. For small systems, we can directly calculate it. More generally, for large systems, we can use direct methods such as LU decomposition, since a Y matrix is usually symmetric unless there are phase shifters. Or we can also use iterative methods. In practice, we can skip the above steps and write admittance matrix directly by inspection. Each row and column corresponds to a node. The calculation for diagonal terms are summation of all the branch admittance connected to it, and off-diagonal terms are negative mutual admittance between nodes. If you want to include voltage sources, just transform them into their Norton equivalent so that they can be treated as current sources. In computer programming, we can automate Y matrix calculation by using network incidence matrix A. The A matrix is an n by n matrix. Usually for each branch, we are given the departure node and the destination node, which can generate the A matrix, and we are also given the branch admittance. From node voltage, we can obtain branch voltage by using the transpose of A matrix, and then obtain branch currents, and next obtain node current injection by using A matrix again. Finally, from this equation, we know how to calculate Y matrix. Because the reference node is also involved in A, we need to manually remove the line and column related to reference node in Y matrix, or otherwise Y will be non-singular and V is not unique. Finally, from the pi equivalent line or transformer models, if we want to include shunt capacitance, we can add this diagonal term because they are all to the ground. And according to what we learned before, we can easily add new terms to the already formed Y matrix like this. Shunt susceptance at each node is a half of the corresponding branch shunt susceptance in the vector B. At the end of this video, I'd like to talk a little bit more about sparsity and singularity of the Y matrix. First, sparsity. The Y matrix is generally sparse, and its off-diagonal terms are non-zero if there is direct connection between corresponding two nodes. This is not true for Z matrix. Why? As the definition of Y at J states, let's excite node J with 1 volt and ground all other nodes. There will be a current starting from J, and as long as the current travels to a neighboring nodes, say node I, it will then go to the ground and not travel to other nodes because it has access directly to the ground. That is to say, only directly connected nodes of node J will be detected with a current. But if there's no direct connection between I and J, for example J only have direct connection with this node, then the current will flow from J through this node to the ground, and no currents will be detected here at node I. Therefore, the Y matrix is sparse. What about Zij? Let's inject 1 ampere at node J while keeping all other nodes open-circuited. Since all the nodes are connected to the whole network, as long as they are not short-circuited to the ground, their voltages are typically non-zero, no matter whether it's a node directly connected to J. Then the voltages at these nodes are non-zero. so the day matrix is not sparse. Finally, let's talk about singularity. If we have n nodes including a reference node, then the rank of the Y matrix is n-1. So the Y matrix is non-singular if we delete the row and column related to reference node, and its rows or columns will be linearly independent. This is generally true unless you have two parallel connected short-circuited lines, or parallel connection of two ideal inductors, or two ideal current sources, or you have two open-circuited lines in series, so there is a floating node. The result is that you have two nodes connected to the same set of branches in the same way. So the system is underdetermined and the Y matrix is singular. In such cases, we can combine nodes into supernodes or add very small or large resistors to make the Y matrix non-singular. Thank you for watching, and in the next video I'll talk about fault analysis.